And we will deal with real gases. So, what happens when gases do not follow ideal behavior? So, at higher pressure and lower temperature, ideal gas behavior breaks down. And even at STP, which is 0 degrees, so some gases are behaving not ideally at 0 degrees and 1 atmosphere. The ideal situation is that we would have 22.41 liters per mole. This is that molar volume that was in one of the earlier videos. So this is just if your gas is behaving perfectly ideally, the volume per mole should be 22.41. H2 has a molar volume of 22.42. So that's actually quite good. Helium 22.41, nitrogen 22.40. That's not too bad. That's almost perfect. NH3 22.40, CO2 22.31. So we're deviating a little bit more. Cl2 is 22.06. So that one's even farther off. The behavior that we see, it's affected by particle size. So, right, the inability to ignore this particle volume that we have been ignoring for every other part of this section, and something called intermolecular forces. So we will spend a lot of time on intermolecular forces next semester, but they contribute to this discussion of gases. So we're going to talk about them here. Intermolecular forces are attractive forces felt between the molecules. It makes a low temperature collision not elastic. So it's sometimes called the stickiness of the molecules. So at low temperature, when these molecules run into each other, the attractive force, this intermolecular force, may make them want to stick together. They may still bounce apart, but not with perfect energy conservation because, right, some of it went into breaking that attractive force that it had to overcome to not stay stuck. So if the intermolecular forces are strong, the molecules are stickier and they deviate more from ideal behavior. So we will use the van der Waals equation for real gases. This is also only one of the few equations that exist for dealing with real gases. In this one, you can see I have it structured here kind of like PV equals nRT, but you can see the correction factors that are in here. So for the pressure, this A times N over V squared, the volume is corrected by subtracting N times B. Those A and B values are characteristics of the gas. So they're values that we will look up in tables or that I will have to give to you. The B value scales with molecular volume. And you can see like where B is in the volume of the gas. And we're subtracting N times B. So we're saying, oh yeah, my gas actually does have some volume. If I wanted to give you the real volume of the gas that takes away the space that is occupied by the actual molecules, I'll subtract the number of moles times this factor. That tells me how big my molecules are. The A value scales with the strength of the intermolecular forces. So the pressure is what is mostly affected by this. So the pressure, the intermolecular forces, if the molecules are sticking together a lot, it's going to bring the pressure down. And so we'll see that. I think I have a picture that we're going to go through. Nope, I don't have a picture that we're going to go through. We can pull up a picture in class. All right. So I do have some example values for you to see here. I just have the A value. So the B value scaling with molecular volume. I think with what we know about atom size and with the structures that you've drawn so far, that one will kind of make sense. But the intermolecular forces, since we haven't talked about them, just so you get an idea of the range, something like SO2 has this A constant equal to 6.71. And the units here are atmospheres times liters squared per mole squared, which is weird, but right, it works out in our equation to give you atmospheres so that you can add it to the pressure. Um, Water, the A constant is 5.46. So whatever is going on in SO2, those molecules, they like to stick to each other more than the water molecules do. I think this is what this is telling us. Carbon dioxide, 3.59. And just so that you can see, like, this is really a big range. Helium, 0.034, right? And helium was something that we saw behaved pretty much ideally. And you can see that reflected in this constant that is not going to take it very far from its ideal value.